Yeah.
What kind of adapter is that? What's plate? Is that HDMI port that's plugged in? Or that's a plate HDMI? I'm shaking. Unlikely I'll play this.
No.
I think Kim actually showed us.
Ah.
Is there anything that you'd like me to say in the intro?
I know this. That's fine.
Okay, cool. So I'm going to read out your brief. I'm going to read there. All right. Your introduction.
Oh, yes.
All right. Hello, everybody. Welcome to this talk, implementing an HPy backend for Python by Detoy. So Detoy is an MSc student at UCT in Cape Town, South Africa, and his research focuses on creating a backend for Python that uses the new HPy API to bind C code to Python rather than existing C API. Yeah, please welcome Detoy.
Hello, everyone. So my name is Detoy. I'm a master's student, and today we'll be talking about implementing an HPy backend for Python. Okay, so first we need to see where we are in the Python world first. Okay, so as you can see here, the Python world is very complex. It's just a part of it. So at the bottom, you have your Python implementations. These are all just different programs that can run Python code. And then there's two main ways of interacting with these interpreters. You can either have files written in Python, so just any Python file you write. Some libraries are written in Python you can also use. But you can also interact with C code. Obviously, the Python interpreter can't just run C code straight out of the box. So what you use an API to connect the C code to the Python code. Currently, the standard is a C API, but then we also got HPy. But we'll get to all that later. So first, what is a Python implementation? A Python implementation is any program that can run Python code correctly. So that's all the only requirement. We can do anything they want apart from that. So we can have different memory management strategies. Some can be interpreted, some can be compiled, some can use just-in-time compilers while interpreting code. They can lay out objects differently in memory. So as you can see, there's inside of these implementations, they can very much decide for themselves what they want to prioritize. So this research focused mostly on CPython and GraalPy. So just like the previous talk, we will sadly not be talking about PyPy. No hate to PyPy, we love PyPy. I'll explain more about that later. Okay, so first, what is CPython? CPython is a reference implementation of Python. It's the one you've all most likely used. Although if you were at this conference, you'll almost certainly definitely use it. Yes, and it is written in C, hence the name. It is only interpreted, so there's no other funky things going on in the background. And it uses reference counting for its memory management with a cyclic garbage collector on top. No need to worry about that. But the main thing you need to know is it does garbage collection mainly by having objects hold references to each other. And also the Python also exposes the C API, which is, as I said, the API used to bind C code to Python code. Okay, the C API comes from CPython, so it is quite closely tied to it, but we'll talk more about that later. Secondly, we have GraalPy. Now, GraalPy is a Java-based Python implementation developed at Oracle. Now, full disclosure, as part of my master's research, I did an internship at Oracle, and Oracle also funded some of the research, so just so you're aware. There's no bias there, just so you're aware. Okay, and GraalPy forms part of a larger GraalVM project, which is a specialized JVM being written by Oracle. Yes, so the GraalVM has a JIT compiler in it, so a just-in-time compiler. What that means is that as GraalPy interprets a code, it will identify parts of the code that are run frequently, compile them as it's running, and then when it runs that code again, it will use a compiled code instead of just using the bytecode it normally uses. And its memory management is based on the JVM. Details on this are very hard to find. Trust me, I've tried for my thesis, but it's based on JVM memory management. I think it might be proprietary Oracle information. So, no further details on that, unfortunately. Okay, now we have the C API. Again, this is the API that connects C code to the Python interpreter. Now, this may sound like a weird esoteric use case, but it's actually incredibly commonly used. Many of the most widely used libraries use this. So NumPy, TensorFlow, SciPy, Matplotlib, any of the libraries that you can use that make your code so significantly faster while you are using it, to probably use the C API. So of the top 200 packages on PyPI, about 40 use the C API to some extent. Yeah, so it's quite widely used. And as I also said, this is exposed by CPython. So the C API originally comes from the API that's used inside the CPython interpreter, but you can also just use it yourself, and then you can gain access to the CPython interpreter. Therefore, it is very, very closely tied to how CPython works internally, and not to how GraalPy works internally. So when GraalPy has to run their C API code, it has to pretend to be CPython, essentially, on top of its own internal structures, in order to be able to run this code, which makes it incredibly slower, whereas GraalPy is typically quite a lot faster than CPython. So you can see this here. So you have a diagram. So you can see you have that code from a C API, but if it runs on CPython, it's very great and fast, whereas if it runs on GraalPy or PyPy, it is significantly slower. So while GraalPy and PyPy are typically a lot faster than CPython running pure Python code, when they run the C API code, they are significantly slower than CPython. But not all hope is lost, because we have HPy. HPy is a proposed alternative to the C API. So its main thing is it is more generic. It is not as closely tied to CPython as the C API, so that when you run it on GraalPy or PyPy, you don't incur these use losses in performance. However, it aims for no loss on CPython, as I'll explain later. However, this is quite a new system, and it's not been benchmarked incredibly well yet. So that's part of what we are doing. Okay, so the way HPy is fast is for a few ways. So one thing is, as in the C API, you have references. So as you mentioned, reference counting, the objects hold references to each other, and this reference is just a pointer to the memory address of the object. However, for GraalPy and PyPy, the memory manager the garbage collector moves objects around in memory. So when you have pure pointers, you cannot move things around, because then you would have to go to every reference to this object and change where it points to, which is unfeasible. And many other things like that CPython does, that C API does, and then therefore makes the C API go terrible on GraalPy and PyPy. Okay, so HPy comes with 3 compilation modes, so ABIs. So what is an ABI? Just an API, but instead of being the source code to another sort of going from source code, it comes with a compiled code. So a compiled code interacts with the system. Okay, and HPy has 3 different ABIs. We have the CPython ABI, the Universal ABI, and the Hybrid ABI. So first, what's the CPython ABI? Well, simply you take your HPy code, and then as it compiles, it literally just sends all HPy functions and variables and macros straight into the equivalent macros and variables and functions in the C API. And when you compile that, you get the exact same thing you have on the C API, where it's great on CPython, but terrible on GraalPy and PyPy. And this is how HPy is theoretically able to maintain equal performance to the C API on CPython. Okay. Secondly, we have the Universal ABI, which, as you can see, is just straight HPy, and it's neutral with respect to implementation. So it works equally fine on CPython, GraalPy, PyPy. It doesn't prefer one. It doesn't disadvantage anyone. And then lastly, we have the Hybrid ABI. So the Hybrid ABI is what you use when you are still busy porting a C code from using the C API to HPy. So if your file is half C API, half HPy, it still works. You just have to use your Hybrid ABI. And then the parts that are written in HPy function as a Universal ABI, and the parts that are written in the C API, it still works as the C API does. Okay, now we get to Cython. Now, what is Cython? Cython is a program that compiles Python code to C code. Okay, and the C code can then be imported in your Python, and then you can run it as an extension. So if you have just a function, so if you have this Fibonacci function and written in Python, you can compile that and import it, and then you can just have a module that has a Fibonacci function in it. But it'll probably be a lot faster because it's written in C and not in Python. Okay, so as you can see here, it takes your Python files and routes it via the C API to C. Okay, so that's important. Cython uses the C API. Yes, and because it uses the API, it has the exact same benefits and drawbacks. Great on CPython, terrible on GraalPy. Yes, so Cython also has another thing that makes it great for CPython and terrible for GraalPy, that internally it is incredibly optimized for CPython, where it doesn't just use the regular C API, it also uses parts of the C API that are intended only to be used inside the interpreter of CPython. But ever since the Cython project is quite well maintained, they think that they can afford to just have to change a code frequently if that gives them a significant performance boost. This also makes it terrible for GraalPy, so it would ties the code even more closely to the interpreter, to CPython. Yes. So what we're doing in our research is we're replacing the C API of HPy inside Cython. Okay, so wherever Cython files normally use the C API, we will change the C API to HPy. This will allow these libraries to run much faster on GraalPy, and it will also allow us to create many different programs we can use to benchmark HPy. Because if we could just have a Cython compiler, we can just compile many different Python programs rather than have to port each one individually. Okay, so in essence, our project is doing this. We're going from this over here to this over here. Okay, now, before we go any further, just a note on PyPy. Okay, so the reason we're not benchmarking on PyPy is because as we worked with HPy in Cython, we saw there are things missing in HPy that we needed to add to make the Cython port work. And we added these to HPy. For CPython, it's quite simple then. You can just, because on CPython, HPy is just a module, just import and you build for yourself. But on GraalPy and PyPy, HPy is an integral part of the distribution. So if you download PyPy, HPy comes with it. If you download GraalPy, HPy comes with it. Okay, so because of that, you cannot just make changes and install it. It breaks. So because I worked at Oracle for GraalPy, I could just ask people there, can you add this for me? And they did. PyPy, we were not so lucky. The people I know from PyPy were a bit busy, so we could not get them to add these changes to PyPy, so we could not benchmark our code on PyPy. However, there's no reason it shouldn't work on PyPy. It should work perfectly fine. Okay. Now, we created this backend. The main thing we did was, so HPy is designed to be easy to be ported from the C API. So unless necessary, the only real changes, you just add an H in front of the C API function name and pass in an extra variable, and it works. So in these cases, what we would do is we just create a C macro that if you compile, you can then you can choose, I want Cython to create an HPy library, I want Cython to create a C API library. And then depending on which one you chose, this macro would turn into the HPy function or the C API function. So that way we maintain Python's ability to generate C API code along with its ability to along with adding the ability to generate HPy code. Okay. Okay, so then we did all this, and then so to test our HPy backend, we had created 4 benchmarks. For the first we created, which is just a for loop benchmark, so essentially just for I in range 20,000, just A equals 0, then for I in range 20,000, A plus equals 1. So just a simple for loop. We did this. This is the first simple test of can this actually work. Then we created a Fibonacci backend. So this just recursively calculates a 10 Fibonacci number. We did this to test how efficient function calls were. So Fibonacci, yes, and the Fibonacci float and func all come from the Pi performance benchmarks for CPython. Okay, so these are all just taken straight from there. The float function performs sine, cos, and square root functions on a float, so it doesn't do anything really meaningful, just as a bunch of maths to do the maths to see how fast it goes. So we did this as well because it also has a bunch of function calls, and it imports other libraries, which is the only one that does that. So we can also see how other libraries interact with our HPy backend. And then lastly, there's the Pfannkuch benchmark, which just performs a bunch of array flips and permutations with specific criteria to calculate the minimum amount of flips needed to satisfy certain conditions. Sorry. Okay, so these were our 4 benchmarks, and each benchmark was run on 5 different configurations. So first, 3 times on CPython, 2 times on GraalPy. So first, CPython with C API. This is our base case. This is what we want to beat. Then we have CPython of HPyCPython ABI. Remember, this is the ABI that is designed to be good on CPython. So this is HPy code that just essentially pretends to be the C API. And then we have CPython with the HPy hybrid ABI, which is, again, the code you use to when you are busy porting something because not everything's ported yet. Okay, we couldn't use universal ABI, the port is not complete, so we use a hybrid ABI instead. However, when you use a hybrid ABI in a module that is mostly HPy, it works as the universal mode essentially. We also ran GraalPy twice, GraalPy with the C API and GraalPy with HPy hybrid ABI. Okay. So our first benchmark was the for loop benchmark, and also these graphs, there are 2 graphs because there's a very big time discrepancy between these benchmarks. So the first graph just shows everything, and the second graph is a zoom in on the column on the left. This appears in all the benchmarks. So then if you go to the second graph, you can see the axis here is just a zoom in of this on this column. Okay, so but first for the for loop benchmark, what we see is we see that GraalPy C API is terrible as we expected. Like I said, GraalPy is terrible when running C API code. Sorry. Okay, but then if we zoom in, we see that actually GraalPy with the HPy hybrid API outperforms CPython the C API, which is incredible for us. Because, again, this is the thing to beat. CPython on the C API is incredibly efficient. And also, when you include the optimization Python does, it's quite nice that we managed to beat this. And also, if you check, this is a peak here of around 2 milliseconds. And you go back, this is around 0.3 seconds. So that's an increase of about 150 times. Okay, when you check on CPython here, you can see that HPy does not perform as well as the C API does. And again, this is because CPython is very, very optimized for using Python, is very optimized when it uses the C API on CPython, which we obviously cannot replicate on CPython on HPy because, again, these optimizations come from inside the CPython interpreter, and replicating them in HPy would break the entire design philosophy of HPy. Okay. When you can see the HPy hybrid ABI is slower than the CPython ABI. As expected, it's less specific, it's not tailored to CPython like the CPython ABI is, so it would make sense that it is slower. Secondly, we have a Fibonacci benchmark. Okay, as you can see, again, GraalPy C API is slower. This is a trend we will see everywhere. Okay, but we also notice that GraalPy running HPy is not 150 times increase, it's about a 6 times increase in performance. Okay, so not as great. So we would wonder, why is that? Well, it's because, as I said, the Fibonacci benchmark tests calls, function calls. And function calls in HPy, we have found are very, very slow when compared to the C API. So when you profile this benchmark, about more than 2/3 of the time of this benchmark was spent calling functions. Yes. Sorry. Okay, now if we zoom in on the right, we can see that HPy performs a bit more terribly than on the for loop benchmark. There's no overlap between these, as was before, and this is also more than the CPython API is more than twice as slow as the C API, which again is not what we wanted. Oh wait, I thought. Sorry. Good. Okay. So we can see this is more than twice as slow as the C API, which is not great. We want it to be equal, but it is not. Again, because of its optimizations and because HPy is calling it, and because HPy's calling functions are very slow. Yes, so because we call so much in this benchmark, we just lose all performance. Now in our next benchmark, float, it is even worse. You can see here we're not even doubling the speed on GraalPy when you go from the C API to HPy. Not great. Yes, but at least we're still increased, but that is good. But again, this is because we call a lot of functions, and because we call a lot of functions in the float benchmark, and B, we also import other libraries which use the C API into this. And because they use the C API, they negatively impact performance. Because even if most of your codes, if all your codes in HPy but use other codes in C API, terrible again. Okay. Now if we zoom in again on the column on the left, we see much greater distinction between the C API and HPy. So previously, if we go here, you can see that there's quite equal distribution between the three, whereas here the difference is much more pronounced. And the reason this again is that while both call functions, this one also has a C API in it, so it shifts the HPy to the right because less of the code is actually written in HPy. Okay, and lastly, we have a Pfannkuchen benchmark, which is just array flips, mostly. Okay, and here we can see that unlike the previous float benchmark, we are performing about 6 times as fast. Now, this is very good news for us because this is by far the most complex benchmark we ran. Yes, because the first two were just about 5 lines of code, float about 20, and this one's about 100, I think. Yeah, so it's much more complex, so that's good. It shows that it's not just a function of the performance decreases or complexity increases, there's more behind the scenes. And while this function also calls things, it's less pronounced, and therefore the performance decrease based on that is not as bad. If we zoom in again, we see again a more equal distribution between the ABIs. Still not what we want, where we want them to be equal, but when you compare it to this, there's much more equality. And also if you check on the axis, it's much less of a performance increase. So go back here, this is again, so if you check here, the CPython API is about 3 times as slow as the C API. If you check here, it's not even twice as slow. Okay, so what did we learn from this research? So firstly, HPy can improve Python library performance on GraalPy. Important, it shows that this idea does work, just maybe needs to be optimized somewhat and more code needs to be ported, but in concept, this can work. Okay. Also, HPy on GraalPy can equal the C API on CPython, as you saw in the for loop benchmark. That is when we don't do things that HPy hasn't yet implemented in a very efficient way, like calling or simply just using other libraries that still use the C API. So if we don't do things like that, we can meet the design goals of HPy of firstly improving performance on GraalPy and equaling the C API on CPython. Okay, but in a broader sense, HPy does not meet the performance expectations we wanted on CPython. It is, in almost all benchmarks, significantly slower than the C API. Now, for our project, that's not too bad, because if you had a pure HPy module, that would be a bit of a deal breaker, but because of the way we implemented our backend, you can still opt just to compile the code for the C API instead of for HPy, and you have none of these issues. So if you have a Python module and you want to use it on CPython, maybe compile it with C API, otherwise compile it with HPy, and you get the best of both worlds. Okay. So in general, HPy is worth pursuing because CPython's optimizations with C API on CPython, the Python's C API optimizations on CPython R is a very special case. Sorry if I mix up CPython and Python a lot. It happens to the best of us. Okay, yes. But there's still more work to be done on the HPy backend for Python in the end. Okay, now I'd just like to acknowledge my supervisor, Professor Cattell here, as well as Oracle for funding my research, as well as allowing me to do a research internship. Okay, you can check out my work here, or you can just contact me here. Okay, thank you. Yes.
All right, we've got some time for questions and a gift.
Thank you.
Great. Firstly, thank you for the talk. It's very interesting to see actual numbers backing up sort of performance claims. You mentioned you had to add some features to HPy in order to do this port. What sort of features were those?
Okay, so the main one we had to add was, so in Python you get slots, so we're not sure what they're essentially just like functions, but like you assign a specific location memory to that function if it's quicker to call. So there's a specific slot, TP desker get. I'm not entirely sure what it does. The documentation is not even very clear. But essentially, in order to run Python's doc tests, you need to have this slot enabled. Because Python you passes the doc string through this slot. So in order to be able to run tests, you actually need to have this. We have to add this to it. And HPy did not have this slot enabled because no one ever uses it. There's the main, also a few other things like adding like dict type object, but that's nothing else was major.
All right.
Thank you. Very interesting talk. I have two stupid questions. One, what is HPy written in? If GraalPy is written in Java and CPython and C, what is HPy written in, and where does the H come from?
Okay, great question. Okay, so HPy is written in C because it's meant for the C API, but that's just like the top layer. So when you run it on, it depends on what you run it on. So if you run it, let's just go back here. So to the ABI. So if you run it on the CPython ABI, it just turns to C code. Whereas if you do run it on universal mode, it depends on implementation. So because GraalPy is written in Java, the way it will interact with the GraalPy as though it was written in Java. So it will like mold itself to whatever implementation you're using it with. And on PyPy, it'll be more Python-y. So the implementations are responsible for implementing how they handle HPy. So again, that is why we could not just add things to PyPy. We need PyPy to add things. Okay, and then what is your second question? Okay, so the H comes from handle. So because that's one of the main things, that instead of having references to objects, you have handles, which is just like a layer of indirection. So that when like moving GC like PyPy has moves objects around, you don't have a roll pointer. You can use this layer of indirection, so it's easy to change like where the pointer points to, essentially.
Thanks for the talk. That's probably a bit tangent, but does HPy play well with PyBind 11, or is that only for C API?
So there's currently no HPy mechanism to use PyBind 11.
Okay.
Yes, so it's actually one of the other topics I could have done. Yes, but it's definitely a thing we are looking at.
Quick question. Your results for the C API are strongly peaked, but the others have a much broader distribution.
Yes.
What's the reason for that?
Yes, that is. I'm not entirely sure. I have checked this before. I've tried to analyze this. My general thing would be because HPy is a bit more, I wouldn't say oblique. It's a bit less like sharp because with the C API, just like call this function, call that function, call that function. Whereas if HPy has more layers of indirection, so my guess would be it comes from that like is less deterministic how it performs. But I'm not entirely sure.
Any more questions? Going once, going twice. All right, thank you to Toy. That was great.
Thank you.
We'll leave it as lunch now.